Okay, so here's some word problems, students, that people are having a little trouble with, and let's see if we could work these problems out. In 2000, the world population was estimated to be 6.11 billion people, and in 2010, the estimate was 6.909 billion people. If the world population continues to grow exponentially, estimate the total world population in 2020. All right, so a couple things about this problem. First, I would sort of do a little timeline here, okay? A timeline. In 2000, this is time, it was 6.115, 6.115, and a little sloppy there. And in 2010, there was 6.909, 6.909. Now, if the world's population continues to grow, estimate the total population in 2020. Well, we could guess. How about it went up by 8, let's say go up by 10, 7.9, but we have no idea, okay? We need to find that value. We need to find that population, if you would, okay? So what we're going to do is we're going to say this is time 0 when we started, this is 10 years, and then this is 20 years from where we started. All right, also we're going to recognize that we're going to use this formula. A is equal to the initial amount, e to the kt. Okay, so that's a very important formula in exponential growth problems. Now remember, if it's growing, k is a positive number. And please round to 4 decimal places. That would be wise. Now, so what we're going to do is find the model, and then we're going to use the model to answer the question. Let's begin with the first step. We know that the initial amount was 6.115 billion. Okay, we know that. And we also know that we don't know k, and we don't know time. However, we do know that it grew to 6.909, okay? And it took how many years to do that? It took 10 years to do that. So 10 is the time, and k, we still don't know. Now, what we can do, we could use this expression right here, okay, to find k. And the way we're going to do that is we're going to divide 6.909 by 6.115, and we're going to end up with this. Now the next step is to understand the only way to get to the k would be take the ln of both sides. So we're going to take the ln of this expression, these two numbers here, okay? And we're going to set that equal to the ln of e to the 10k. Now we know that ln is log base e, or better yet, we know we could use the power rule to move that to the front, okay? So what do we have? We have the ln, of, something over something, okay, is equal to 10k times the ln of e. Now the ln of e is just log base e of e, that's just 1. So this right here is just 1. So it just is 1 times 10k is just 10k. And so then what we're going to do is we're going to divide both sides by 10, and we're going to find k. Now what I'm going to do is I'm going to take that, I'm going to put it in the calculator. I'm going to hit ln, I'm going to get a parenthesis, and I'm going to write 6.909 divided by 6.115. Then I'm going to close my parenthesis and hit divide by 10. Okay, now I'm going to do it with my calculator now. If you have trouble, you could just do that a step at a time. That's no big deal. So ln of 6.909 divided by 6.115, close parenthesis, divide by 10, and I get the following number. k is equal to 0.0122. See how I rounded to 4 places? Now I have my model. My model is A is equal to 6.115 times e to the 0.0122t. Now, can we answer the question? The question said, estimate the population in 2020. Well, when we say 2020, we're going to plug in t equals 20, okay? So we're going to say A is equal to 6.115 e to the 0.0122 times 20. Now remember, when you put that in your calculator, make sure that you put it in correctly. 6.115. Then I'm going to hit second lin, and I'm going to write 0.0122 times 20. Close parenthesis and hit equal. And I have 7.805. What does that mean? That means the world population in 2020 would be that many billion people. That's a lot of people, okay? Makes you think about things. All right, that's question 25. I hope that answered your question. Number next. I call this a Randy Travis problem, because he was digging up bones, exhuming things that are better left alone. Maybe that joke was left alone. I don't know. All right, if a bone is 100 years old, what percent of its original amount of carbon-14 do we expect to find in it? Now remember, the half-life of carbon-14, I think, is 5370. I better go check that. Okay, I'm back, okay? Now look, I want to explain this, okay? Let's say someone has $100 and they go through half their money in one day. After one day, they have 50. I don't know why I had a percent there. After another day, 25. See, you get the idea of half-life? Now, we have a question that says a bone is 100 years old. What percent of its original amount of carbon-14 do we expect to find in it? Well, the way this works is when something dies, there's 100% of the carbon-14 there, and in 5,370 years, 5,370 years is going to be half of it left. Okay. Well, obviously, if it was only 100 years old, it's going to be very close to here. I'm assuming a pretty big number. If this is 100, and that's 0, I'm thinking like 99 or something. We'll see. So again, you're going to start with the formula. Now, first of all, we got to find K. So if I start off with my whole amount and I end up with half of it left, and it took 5370 years to do that, I could find K. So K on our calculator is going to be the ln of 0.5 divided by 5370. While I'm reaching for my calculator, do kind of keep in mind that it's going to be negative, right? Okay, now I have a very, very, very small number, okay? Negative 0.123 zeros. I would do at least 3 decimal points past the 3 zeros, okay? All right, that was a mouthful right there. Now let's go back to our model. Our model is the amount of something. What we started with 100%, and e to the kt. So it's going to be negative 0.000129 times time. There's our model. And the question said, how much is left in 100 years? What are we going to plug in for t? We're going to plug in 100. Now I'm going to get my calculator out. I'm going to hit clear. And I'm going to do 1 times e to the negative 0.000129 times 100. close parenthesis, and hit equal. And I have the following number, 0.8789, which is really 80.88, which is really 88%. Okay, so keep that in mind. That's how to do that problem. Okay, another question. Find the amount of time it will take for 10% of an initial sample of plutonium-239 to decay. If 10% decays, then 90% will remain. That's a hint, okay? So let's see if we could do this problem. Okay, well, let's talk about this problem. Plutonium. Now, plutonium-239 has a half-life of 24,000 years. So keep that, thought in mind right there, okay? We're going to start off with this model. We're going to use the information to find K, and I found K is negative 0.0000288. Or you could say 289 if you wanted to. Now here's what's going on. At time equals 0, there's 100%. At 24,000 years, there's half of it left, or 50%. Find the amount of time it will take for 10% to decay. That means if 10% is gone, 90% is there. So we want to know that time. Obviously, it's less than 24,000. How about we guess 10,000, okay? All right, could we find it? Yes, we can. Okay. So I'm thinking that I just explained this, but this is our setup. We found K. And this is what's going on with the problem. So here we go. We're going to have 90 or 0.9 if you want to do that. 0.90 is equal to 1.00 e to the negative 0.0000288. Okay, and we want to, and that's t. And we want to solve for t. All right, so what did I do? I did the ln of 0.9, then I divided it by my negative 0.0000288. I got 366 years. Okay, I rounded to the nearest year. All right, let's see if we could do the next problem. Okay, here's a problem. Solve for the given variable. Well, here's my equation right here, okay? So A is equal to P e to the RT, right? All right, now we want to solve for t. Can I get t by itself? Oh, that's a very good question. Well, we could use the properties of logs and what we know about solving an equation to do that. So first of all, let's isolate this part. We'll do that by dividing both sides by p. Now I have a over p is equal to e to the RT. I would very much like to get t by itself. Well, the only way to get into this power is to take the ln of both sides. So the ln of a over p is equal to the ln of e to the RT. Now, according to our power rule, we can move that to the front. The ln of a over p is equal to RT times the ln of e. Now, we know that the ln of e is 1. So the ln of a over p is equal to RT. Can we solve that for t? Yes, we divide both sides by r. Divide both sides by r. So t is equal to the ln of a over p divided by r. Okay, I hope that helps you out. So if you are interested in working those particular problems at 15.3, maybe this explanation helped you out. I certainly hope so.